All right. Let me check on you guys. These two gentlemen. There we go. Okay. Let them in. All right, so we're gonna go with this crew for now, and anybody after this point, I'll get them on the second wave. Okay. Oh, no. All right, gentlemen. So today is a lot more smooth. Again, my technique is start the live stream before I let you guys in. I think what was causing me trouble was, I guess, just Zoom was getting overwhelmed with the amount of people on. So then it was having trouble pushing the image. So I was like, okay, let me start the stream first and then let you guys in, okay? So we are here at the top of week 8, right? So I think we're gonna be continuing chapter 3. I think we have 4 sections remaining in chapter 3. We're gonna meet today, we're gonna meet on Wednesday. And then after Wednesday, enjoy your spring break, right? Take some time off, do what you need to do, get some rest, recover, party hard, play hard, work hard, do that kind of stuff. And then essentially the rhythm from here going forward, instead of doing 2 sections a day, we should be able to only do 1 section a day from here on to the end. Okay. As usual, if you have questions, feel free to unmute yourself. That's my recommendation to get my attention. And yeah, let's just kind of get into it. Okay, so I have to go like this. This one, right? Okay. And why does it look like this? But this is fine, I guess. Okay, so we're continuing chapter 3 with applications of differentiation. And so today we're going to be working on section 3.5, optimization, business, economics, and general applications. The objectives here are to solve optimization, which is basically maximum minimum problems using calculus. All right. So, so far, most of our discussion has been on, basically just exploring what do we mean by the derivative. Again, the derivative just being the slope of the tangent line at a point. And then we looked at like different ways to find the derivative and calculate the derivative. And now we're looking at some applications of the derivative, basically an optimization with max and min, finding the max or finding the min, right? So the maximum or minimum should occur, basically is going to peak of the mountain or the bottom of a valley. And that should occur when your derivative is either 0 or undefined, right? So we've kind of talked about how to find those critical values, points of inflection using the second derivative, critical values using the first derivative, things of that nature. Okay. So let's see. So a strategy for solving maximum minimum problems. First, read the careful problem. Read the problem. I was going to say read the careful problem. I was like, what? Read the problem carefully. If relevant, make a drawing. Second, make a list of appropriate variables and constants, noting what varies, what stays fixed, and what units are used. Label the measurements on your drawing if one exists. Third, translate the problem to an equation involving a quantity Q to be maximized or minimized. Try to represent Q in terms of the variables from step 2. Try to express Q as a function of one variable. Use the procedures developed in sections 2.1 to 2.3 to determine the max or min values and the points at which they occur, okay? So in this example, from a thin piece of cardboard, 8 inches by 8 inches, square corners are cut out so that the sides can be folded up to make a box. What dimensions will yield a box of maximum volume? What is the maximum volume? Okay, so with this one, let's start by drawing a picture, all right? Let's start with a picture. So what I'm gonna do, let's go to my view, let's go seamless, and hopefully this doesn't throw my device off because sometimes when I add a page, it throws a tantrum. It's looking pretty good. Thank you, device. Okay. So we're starting with a piece of cardboard that's 8 inches by 8 inches, right? So let's see. We're going to start with a flat piece of paper or a flat piece of cardboard, right? It's 8 inches by 8 inches, so it should be a square, right? So 8 inches by 8 inches. Then I think the instructions say that square corners are cut out so that the sides can be folded up to make a box, okay? So let's capture that. Let me copy. I'm going to paste. And what we're going to do, we're going to cut out square corners. So basically something like this, style. That's kind of irking me. Okay, what we can do, style, sticking that up. Yeah, that's better. Okay. Let's copy, paste, paste. Paste. All right. So we have this cardboard and we're going to cut out the square corners like this so that we can fold up the sides to make a box, right? Let me see. What dimensions will yield a box that maximizes the volume, and then what is the max volume, right? So we don't know the dimensions here, right? So we don't know the dimensions of these square corners that we're cutting out. All we know is that all the lengths or all the sides are the same length, right? So then when we're done, we're gonna fold. Let me paste. We're gonna fold up the flaps so that we can make a open box, all right? Square corners are cut so the sides can be folded up to make a box. And then we want to know the dimensions that's going to maximize the volume, okay? So when we cut out the corners, let me just draw a picture there. Let me see. So something like, okay. Let's see. Yeah, about like that. Okay. Connect it there. There. I think that's all it should be. Undo. There. Okay. And then let's do partial like that. And we're just gonna cut it there. Here, okay. And then this one. Let's see if I do style. Okay, let me do this. That, like that. If I do style, I want that to be a dashed line. That's good. Style, dashed. Okay. Right. So in the final drawing, if the line is dashed, that's because it's behind the flap, right? So we have like a 3D box where we folded up the flaps, the size, and it's like this, right? So now if we label the different components, so this is going to be the X that we, the X that we had in the above picture, right, where we cut it out. That's going to create our new height. This side here, right? So that side corresponds to this guy right here, which is going to be 8 minus 2x, okay? So this guy here is going to be 8 minus 2x. And I think this one also is going to be 8 minus 2x, basically from here to here. Okay. This one runs from here to here, like that. Okay. And this X runs from here to here. Okay. So again, if anything is not clear, just stop me and I'll get. I'm pretty sure I should have some people in the waiting room. They should know by now. If you don't catch that first wave, just wait until the 15-minute mark. You have to just wait. Okay. So again, we want to maximize the volume, right? So if we're talking about volume, let's go ahead and write an expression for volume. So for an image like this, the volume is going to be what? Length times width times the height. Okay. So if we insert what we have, so our length is going to be the 8 minus 2x. Our width is also going to be the 8 minus 2x. And our height in this case is x. Okay. Let's see. Let's go ahead and expand this guy. So if we FOIL 64, 16 plus 16 is a negative 32 x plus 4x squared. But then we also need to distribute the x. And so basically this is going to become an x, it's going to be squared, and this is going to become cubed. Okay, if we distribute that second x, okay? So here's an expression for our volume. So then in order to, and I'll just kind of work over here for right now. So our goal is to maximize the volume. Okay. So that's going to occur when the derivative of our volume is either 0 or undefined, right? So we need to find the derivative, set it to 0, find those critical values, verify the critical values, and then we can either use the second derivative to identify it as either a max or a min, or we can do the first derivative test to say, okay, is it going from increasing to decreasing, or is it going from decreasing to increasing to identify it as a max or min, right? Okay, so so for our v of x, right now we have this 4x cubed minus 3x squared, 32, not 3, 32x squared plus 64x, right? So let's go ahead and find the derivative. So v prime, 4 times 3 is 12x squared minus 64x plus 64, okay? So to find our critical, now again, this is a polynomial, so it'll never be undefined. So that leaves the only candidates for our critical values are going to come out when we set the derivative equal to 0. Hey Siri, no, that doesn't work. I think we can divide.
Web results. I can show them if you ask again from your iPhone.
Let's see. 6 and 4 is 10. Hey Siri, what's 64 divided by 4? 16
divided by 4 is 16.
Okay, so we can factor out a 4 from every term here. We're going to get 3x squared minus 3x 30 plus 24, 16. Okay. All right, so to factor this guy, we're looking for two numbers that multiply to give us 48, right? Two numbers that multiply to give us 48 and add to give us -3, right? The 48 comes because I said the 3 times 16, 30 plus 18 is 48, right? So two numbers that multiply to give us 48 and add to give us -3, right? Now 48 is 2 times what? 24, but then that's 2 times 12, but that's 2 times 6, but then that's 2 times 3, right? 16 times 3, right? Okay. So then all I'm going to do is go through all the combinations and stop at the line that gives me a -3, okay? So for instance, all the combinations of the factors are going to be 1 and 48, but that adds up to 49. So we're not looking for those two. We can do 2. Now notice, if we use a 2, what's left over? 8 times 3 is 24. But those add up to 27, so we're not looking for those guys. We got a 3, right? I'm just on the left, I'm just going 1, 2, 3, right? So if we use this 3, what's left is 16. But those add up to 19, so we're just going to keep going. There is a 4, right? There's a 4 right here. If we use this 4, what's left over? 12. Yep, 4 times 12. So then 4 and 12, but those two add up. They give us, what is that, 16? Let's keep going. There's no 5, but there is a 6 right here. There's a 6 here. If we use that 6, we have 8 left over. So it looks like 6, right? 6 and 8. So it looks like nothing adds up to, we don't get any integers. 6 and 8. I think those add up to, nothing added up to the -3. Okay, so what that means is that we might not have integer whole number results here, but we could use the quadratic formula, right? So we tried to factor to get integer results. We didn't get any integer results. So then let's just try the quadratic formula. All right, so I'll just do the quadratic formula here. The way I remember quadratic formula, x equals, let me see. The negative boy couldn't decide to go to the radical house because he was square, so he missed out on 4 awesome chicks, and it was all over by 2 a.m. That's one of the students showed me that years ago. As soon as he said it, it like was ingrained in my mind because it was like a mini movie or a mini story. So that's how I remember quadratic formula. So now I just use it that way, right? So now if we use the quadratic formula, then x is going to be 3 plus or minus the square root of 9. 9 minus 4. Our a is 3 and our c is 16. Oh, okay. If we're getting maybe there's no solution. It's raised up. Did we do something wrong? Maybe we missed something somewhere. Let's see. 64. 8 times 2 is 16. Plus 16 is -32. Plus 4x squared. You distribute and it becomes that. Take the derivative, 12, 64, 64. Let me see. Because we're getting a non-real solution there for critical value. Did I keep my negative? Negative b plus or minus the square root of b squared minus 4 times a times c. AC here. Because we're getting a negative discriminant. What am I missing? Let me see. Give me a second. I'm gonna stop in just a moment to let these guys in. I was trying to wrap this one up. Let me just do one more scan. Then piece of blah 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 8 by 8. What are the dimensions of the maximum volume? What is the max volume, right? So if that's 8 inches, 8 minus 2x, yeah, that's good. 8 minus 2x. Yeah, yeah. Okay. Okay. So then when we take the derivative, we get this. Let me check this one more time. 8 times 8 outer, 8 times 2 is negative 16 minus 16, negative 32 plus 4x squared. You distribute that. Okay. 12, negative 64 plus 64. We didn't get any numbers there. Opens up and it's been moved up, so it doesn't seem like it crosses. What am I missing? So let me see. It's never going to be undefined. It's not going to be 0. We want to maximize it. We got a cube. It's usually when the derivative is either 0 or undefined, right? We didn't get a result there. Could be coming like that. Because that's a non-real result. Okay, let me scan real quick. We did all of that. We did that. We got the same thing. Did I make a mistake there? Is that where it is? No, we got that. Yeah. 12. I think I made a mistake there. Let me see. Oh, when I did that factor. No, I got that. 16. Oh, okay. I think I found it. Right. Is it that one? Yeah, there it is. Oh, that's why it's been off. Okay, I found the mistake right here. When we divided by 4, right here, this guy, this should have been what, 16? I would draw it in red. That's supposed to be a 16. That's what I was like, why are these numbers not working out? And I know they should work out. Okay, so now let's go back. I think we're still looking for 48, but instead of two numbers adding up to give us 3, I think I was just moving too fast. We want two numbers to add up to give us 16. And those two numbers are right there, right? So we actually have those two numbers, these two. I'll do it in purple. Boom, those are the two numbers. But then we want negative 16. So let's do like this. Because we want negative 16, then it means it's going to be negative 4 and negative 12. Okay. And again, these were the two numbers that we're looking for, right? Okay, so we got to the bottom. We did make a mistake, and I knew it was in there. I just couldn't find it, but we got to the bottom. So, okay. All right, so let's try to wrap this up. So now we have two numbers that make the derivative 0, right? Okay, so let's finish the factoring. We'll go like this, like this, like this. So then the upper left, we have our 3x squared, and we got our 16 here. But now what we're going to do is rewrite this negative 16 using the two numbers that we found. So we got a negative 4x and a negative 12x, okay? So then we ask ourselves, what can we factor out of these two here? They both have, it looks like an x. We can factor out an x for both of those guys. What can we factor out of these two guys here? It looks like they both have maybe what, a negative 4? Is it negative 4 or just 4? Let's just do 4 for now. I'm going to factor out the negative 4. Let's factor out negative 4 and just see what happens. Okay. And we'll go back and fix the signs if it doesn't work, right? With these, what do these two have in common? We can factor out a 3x. So let's do a 3x. And with these two here, let's do a -4, right? Okay, so our claim is that 3x squared minus 16 factors into 3x minus 4 times x minus 4. Okay, let's see. And then we're going to set it equal to 0 real quick. Let's do a quick check. First times first is a 3x squared. Outer is going to give us a -12x minus 4x is a -16x, right? And then last times last is a +16. So these are the two that work. Okay. So then now that we got it factored, we set each factor to 0 and solve. We're going to get x equals 4/3 or x equals 4, right? So we could look at the second derivative. I'm trying to wrap it up so I can get to these gentlemen in the waiting room. Let me go ahead and find b double prime. So it becomes 24x minus 64. Okay. If we plug that 4/3 into the second derivative, let me see. What is that? 24 divided by 3 is 8 times 4 is 32. So if we plug this first one, if we plug this into the second derivative, it's going to be negative. The second derivative is negative means that the graph is concave down, which means that's a max, right? So this should be a max, a local max. This is one candidate for max. When we plug 4 into the second derivative, what is that? 96 is going to be positive, which means it's concave up, which means this is the minimum value, right? Minimum. We want a max, so that occurs when x is 4 1/3 inches. Just for the sake of time, I'm going to go with that, right? Because we had that hookup. 4 1/3, 4/3 inches, right? Okay. Let me just kind of, again, I did kind of use the notes to try to figure out where I was making my mistake. I was moving a little bit fast, but we got to the bottom of it. Okay, let me copy this. And then let me go to view, single, and I'm getting to the guys in the waiting room, right? So here's a type version of what we did, right? Okay. And I think we got everything. We found our mistake. And then 4/3 are 4. 4/3 is the only critical value from 0 to 4. So now we found the second derivative. All right, it's negative, which means concave down, which means we have a max. And then, so that occurs when x is 4/3 inches, and then the maximum volume, basically you plug that 4/3 into the original, and you get your maximum volume here, right? So I think that part we kind of left out. Okay, quick check, and let me get these guys here. Okay. Okay. Oh, that's a good amount. All right. Let's see. Oh no. Ow, ow. Let's get the student. Okay. This one. Okay. He must have come and gone, but that's fine. Okay, I got that student. Cool. This one. And then this one. Okay. Right here. Cool. Okay, that looks good. I'm just gonna go with it. I think I got all these guys. Let me make sure I got him. Yeah, got him. Okay, let him in. All right. So I'll give that a time to populate. All right, gentlemen, welcome. If you're just joining us, we did get kind of a little bit, we've only done like one example. We're basically continuing chapter 3 on optimization, basically talking about max and min. I cannot get this thing to go. Come on. Okay, there it is. Ugh, okay. I find it, but I find it. So that's what's causing delay. So you've only missed one example, but we are here. Right. Okay. So again, let me see. If you're just joining us, I'm gonna rely on you can have to go back and watch the recording for any announcements. We're gonna keep moving forward. So yeah, we're basically looking at applications of the derivative on optimization, and we're focused on maximizing and minimizing. So here's example 2. Let's get rid of this. A stereo manufacturer determines that in order to sell X units of a new stereo, the price per unit in dollars must be this. The manufacturer also determines that the total cost of producing X units is given by this. We're asked to find parts A through E. Find the total revenue, right? Okay. Find the total profit. Okay. How many units must the company produce and sell in order to maximize the profit? So we want to maximize the profit once we find it. What is the maximum profit? And what price per unit must be charged in order to make this maximum profit? Okay. So what we're going to do, let me add a page. I need about 3 pages. Okay. Let me go to view, seamless. Okay. All right. So let me get a copy. So the price per unit, our P of X, was given as 1,000 minus X, and the cost, C of X, is 3,000 plus 2X, okay? So first we asked to find the total revenue. Total revenue. Okay. So for part A, our revenue function, the revenue is going to be, if we have the price per unit, we're going to say the number of units produced and sold at this price, right? So that's basically going to be X times P of X. That's going to be our revenue. X is going to be our number of units produced and sold. P of X is the price per unit, right? So then if we keep going with this is going to be X times the 1,000 minus X, which is going to become 1,000X minus X squared. Okay. All right, so we got our revenue function. Let me highlight it. Okay. So then we're asked to find the total profit, right? So in business, profit is going to be what? Revenue minus costs, okay? So then B, our profit function, capital P of X, the revenue function minus the cost function, okay? So revenue was the 1,000X minus X squared. The cost function was the 3,000 plus 2X, okay? So then we just want to simplify this guy, distribute, right? We need to distribute this negative here and combine like terms. So then that's going to give us the 1,000X minus X squared minus 3,000 minus 2X, right? I'm just going to put this in descending power order just so it looks like what we're used to seeing. So negative X squared. Okay. So 1,000 minus 2, 998X. Okay. So plus 998X minus 3,000. I think that's it. Yeah. Okay. So this is our profit function. Okay. So then part C, how many units must the company produce and sell in order to maximize the profit? So for C, we are being asked to maximize the profit. Okay. So again, in order to maximize this, if we think about this graph, right? This is a U-shaped curve. The highest power is to degree 2. It looks like an upside down parabola. Now, because we're working with a parabola, you could use college algebra and use the vertex formula and jump straight to the vertex, and that should be the maximum. But since this is calculus, what we're going to do instead is, again, the max should occur at the peak, at the peak, right? At a peak. So we're going to look at the first derivative, set it to 0, and find those critical values. And then, do a test to determine if it's a max or a min, right? So in other words, let's go ahead and find P prime of X. That's going to give us negative 2X plus 998. I think that's it. Okay. We want to set this equal to 0. Remember, this is a polynomial, so it's never going to be undefined. So we just want to find what values of X make this 0. We subtract the 998 and divide by 2. X equals 499, right? So 499 units. But now this is a critical value. We need to do an additional test to verify that it's either a max or it's a max. We could look at the second derivative, right? Or we can, if we use the first derivative, we'd have to choose a x on the left, choose an x on the right. We have to show that the original function is going from increasing to decreasing. I think in this case, I'm just a fan of using, we don't always have the luxury of using the second derivative test, but whenever we can use the second derivative test, oftentimes it's a lot easier to do the second derivative test, right? So let's go ahead and look at the second derivative. In this case, it's just going to be negative 2, right? So that means that the function is negative. With the second derivative just being negative 2, that means that the original function is always concave down. So that since the original function is always concave down, this is a max. All right, this is a maximum value. Okay. So then to answer the question, how many units must the company produce and sell in order to maximize the profit? It should produce and sell 499 units. Okay, let's keep going. Okay, that was C. And then D asks, what is the maximum profit? So if this is the X value that maximizes the profit, then the max profit is going to occur. Basically, you plug this into the original, right? A, B, C, D. So then we want to find P of 499. Okay. I do kind of want to do a quick showcase of Desmos, right? Normally I use my TI-83 Plus emulator. What I'd like to do here, I want to do a demo using Desmos. Type it in over here. So what Desmos is a free graphing utility, for looking at graphs and, calculating crunching numbers and things of that nature. Okay. So let's see. What I want to do here is take my original. So I'm gonna type it as P of X, capital P of X, right? Is equal to, thank you, stop. Now you're throwing me off. I was here. Okay. So our original function, we had our profit function, we have this negative X squared plus 998X minus 3,000. Okay, so we can't see that. We'd have to change the window for it to be able to see like all the parts of it. Let me see. I got to think of a proper window. What was that? Okay. Well, we can't see it here. Okay, see, you have to keep zooming. And like you just got to do an appropriate window to be able to see it. There it is. Okay. How can I go like this? No. Let me see. How can I change the dimensions? I just want to drag this. Okay, I'm not sure how to change the view so you can see it. For right now, I'm not going to worry about that. I wasn't really trying to look at the graph, but I just wanted to type the function in, and I want to evaluate it when x is 499. So that's really why I was calling on this. So then I'm going to do p of 499, and let me see, the maximum profit looks like it's 248,701, right? So when you plug in the 499 into the profit function, so the reason I was pulling this up was so we can just see that calculation, right? You can see it in action. There it is. So the max profit looks like it's 248,701. Okay. Right. Okay, that looks good. Okay. So and we'll come back to Desmos. We'll use it for some other things. But yeah, so Desmos, I know I'm just using that because I know a lot of students use it. So I wanted to start incorporating it in some of our presentations. You've seen me using the virtual TI-83 Plus, and then another resource is called GeoGebra, which is GeoGebra.com. It's similar to Desmos. Okay, so that was D. Okay, and then what price per unit must be charged in order to maximize the profit? This is the profit. Oh, okay. So if this is our max profit, let me see. What, divide this by 499? Yeah, we want the price per unit. So at this price and that many units, then the price per unit is going to be the 248 701 divided by 499, right? That should be it. So then our lowercase p of x should be the 248 701 divided by 499. Hey Siri, what's 248 701 divided by 499?
248,701 divided by 499 is approximately 498.3987.
Price per unit, almost $500. Let's see, is that right? What am I missing? I feel like I'm missing something there. Price per unit. What are we selling here? Stereo manufacturer, $500 a stereo? It could be. What was the price before? 1,000 minus X price. I feel like I'm missing something there. Let me kind of put a pin in that one. Okay, let's see how we did so far. I feel like a revenue function is good. Now they got 80. Where do we, 1,000, where's the 2? 20. Now we put 2. Did I write something wrong somewhere? Profit 2, 3,000. Let's see, the cost function, we got a 2x. Something's off. Let me see. Did we get the wrong? Because sometimes the function doesn't display properly. Cost function right there. I think one of the cost functions is off. Ours had a 2x, but they have a 20 here. And I think it is supposed to be 20. Let me see. Let me make that change and see if I can get the same numbers that they have, right? Let me make that change, right? So I'll note it here. It's just a typo error. I think this is supposed to be a 20, right? Because if we go back to the original, you see it's a 2x, and that's what's throwing us off. Okay. So let's do that cost function. If we did revenue minus cost, then this guy is going to be a 0 there, right? Okay. If we distribute a negative, there's going to be a 0 here. Oops. There's going to be a 0 here. All right, I think that's okay. So then 1,000 minus 20 is what? 980. So then this changes to 980. Okay. Again, this changes to 980. Yep. Maximize the profit. We took the derivative. The 2 comes down plus the 980. So then if we solve from there, we subtract and divide. This changes. Subtract, let me see. So 9 is what, 4? 18 is a 9, 490 units. Okay. Okay. So then this is going to be 490. Okay, so then if we go back to Desmos, this guy changes. This is supposed to be 980. And then this needs to be 490. Okay. All right. I think that's a little bit better. And so anything that we're changing, I'm marking in red. And it was just because we had a typo in the beginning. 239,800. Okay. Okay. All right. And then price per unit. This as well. So we're doing 239,800 divided by 490. Hey Siri, what's 239,800 divided by 490?
239,800 divided by 490 is approximately 489.3877.
Okay, so we're still getting about almost $500 per unit. So then round that to 489 point what cents. Okay. And again, I left it in red because it came after that change that we, that correction that we had. Okay. All right, let's see how do we, okay. So, and let me get rid of these extra pages. This one can go delete. And this one can go, okay. So I think we got that. That looks better. 490, we got the 490. Second derivative is -2. Now they got a 100 there. For 237, 100. I don't think we got 237, 100. Okay, let me see. Maybe I typed something wrong here. Profit function, -x squared plus 980. Oh, I put 300. Man, the mistakes. 0 here, right? Okay. So with that 0 there, now we get the 237, 100 right here. 237, 100. Okay, that's fine. So then right here, this changes 237, 100. Hey Siri, what's 237, 100 divided by 490?
237,100 divided by 490 is approximately 483.8775.
8775. Okay. So then that's approximately 483 and 88 cents. Okay. Yeah, it is easy to like make typos and errors like that. That's why you just have to like kind of take your time. All right, so let me see. 3,000, we got that, we got that, we got that. We got that one. Oh, 490. Okay, let me see here. Oh, okay. So we did get the last one wrong. So for the last one, price per unit to achieve this is, okay. So just use the original price per unit. So you plug the 490 in, so that's a 510. I'm just gonna mark that one as wrong, right? I wasn't understanding that concept. So yeah, this is just wrong. I'm gonna just strike through this. I'll leave it. But basically all you do is P of 490 and you get it from there. Okay. Okay, that was an adventure. Okay, let me check on you guys' Zoom for a hot second. I'm gonna go to view single page. I'm gonna let that be for now. Yeah, I knew I was overthinking that, but it's okay. All right, let's pause here for a moment. I just want to check on you guys. Let's see. Like this. Yeah, let me get these. Let's see one more time. Gabriel. Okay, and I got it here. What's the other student? Oh, he was here. He must have just got left and came back. Okay. Come on, close. There you go. Okay. All right. Let me see. So 7:15. We got a solid 20 minutes. Okay, let's keep going. All right, let's try another one. So here's our third example. So this is on life sciences, concentration of a drug in the bloodstream. A drug is administered in the bloodstream of a patient, right? Let C of T represent the concentration of the drug in the bloodstream in nanograms per milliliter of the drug T minutes after it's administered. What is the peak concentration of the drug in the bloodstream and when does this peak occur, right? So we have this expression for the concentration. If we want to find the peak, in other words, we want to maximize it, that's basically asking us to find the peak of the mountain. In other words, look at the first derivative, find the critical values, determine if that's a max or min, and then that's going to be our max, right? Okay, let's give this one a go. I feel like I'm okay on space for right now, so I'm going to go with it. So the original, seamless. Let me go view seamless, and let me give myself at least one page. Okay, I think that should be enough. All right. So we want to maximize. So the request is for us to maximize this concentration function, this 25 T e to the negative 0.04 T. Okay. All right, so in other words, what we're going to do is take the first derivative, set it to 0 and solve. So then our C prime of T, so it looks like we got to use the product rule. The first, which is this guy, the derivative of the second, E is its own derivative, times the derivative of the power of the exponent, which is going to be negative 0.04, right? So that's the first times the derivative of the second, plus the second, which is this guy, this, times the derivative of the first is just 25, okay? So that's the product rule. So then the goal here is to set this equal to 0 and solve. Or the critical values are going to occur when this is either 0 or when this is undefined. Let me see if I can simplify this down some. Let me see. So they both have this E that we can factor out, and they both have the 25 that we can factor out. All right, so let's factor out the 25E to the 25 times E to the power of negative 0. Okay, I didn't write that one all the way out. That should be a 4T, okay. 0.04T, okay. So if we factor that out from both terms, let me highlight it. So we factored out this 25 and this guy, 25 and this guy, okay? So then in the first expression, we still have this 0.04 along with this T. And in the second expression, it looks like we have a 1 left over, right? So now that we have it in this factor form, two or more things that multiply to give us 0. use a zero factor property where we set each thing to 0 and solve. Okay. So then one of them, we're going to say 25 e to the negative 0.04 t. I don't know why I'm not writing that for t. We want to set that equal to 0. So an exponential function is never going to be 0, right? If we divide, if you have an exponential decay where your y value is 0, right? Because I think it's entirely above the x-axis. So y won't be 0. So no solution there. But then let's try this other one.
Morehouse?
This negative 0.04 t plus 1 equal to 0. Subtract and divide. Subtract 1, divide. Let's let me see. 1 over 0.04. 0.04 is what? 4 over 100. So t equals 100 over 4. That's 25 minutes. T minutes, right? That should be 25 minutes. I think that's okay. Hey Siri, what's 1 divided by 0.04?
1 divided by 0.04 is 25.
All right, okay, let's go with that. So it says, what is the peak concentration of the drug in the bloodstream and when does this occur? So we're saying that it occurs after 25 minutes. We'll just kind of go like this, and then we need to plug that into our original to find the peak concentration. Oh, now, okay, this is our critical value. We need to verify. Now, I feel like we need to verify that this is indeed a max. Now, looking at the first derivative, I feel like it might be kind of tough to do the second derivative test here, right? Because it's kind of a lot going on. So instead of doing the second derivative test, we can use the first derivative test where we choose x on the left or x on the right, and then show that the original function is going from increasing to decreasing, right? So let's do like this real quick. Here's a number line. Here is when here's 25, right? And we want to compare the original, or actually we're going to look at c prime of t. Okay. So when x is 25, or when t is 25, c prime is 0. Okay. Left of 25, we can plug in something like 24. Let me see. So I think I'm going to use Desmos for this, which is here. Okay. Oh, it just got like dark, like extra dark all of a sudden out of nowhere. I know the sun is setting and everything, but I was like, man. Okay, let's put in this first derivative. I'm gonna get rid of this and this. Okay. So then I wonder if we can do derivatives. For right now, I'm just gonna call it C of T. Okay. And I'm gonna assume that what we have is proper 25 e to the power of this negative 0.04 t. Okay. Right there. Okay. And then it's basically times negative 0.04 t plus 1. Okay. So then, let's see. Okay, let's just do a test point. No, can I undo? Oh no, I gotta type on it. There it is. Okay. I just didn't, come on, stop that. Okay, that's better. I just didn't want to have to type all that again. So when t is 25, we should get 0, right? So let's just do c of 25 to confirm. Why aren't you typing here? Is it showing up somewhere else? What's the deal? Why would you type? No. Come on. Let's do it like this. Okay, let's see. Okay. Let's see. I'll go like this real quick. I don't know why my keyboard won't register. There it is. Okay. C of, now we put in 25, we get our 0. Okay, so we can go with that. So then now we want to do C of, so if we're anticipating this to be a max, if we choose an X on the left or a T on the left, then we should get a negative result. That means that, sorry, we should get a positive. That means that the original function is increasing, right? So when we put it in 24, we should get a positive result, all right? So we chose something on the left, we got a positive result. I'll put it like this. We got a positive result, so that means our original function is increasing. When we choose something on the right, we should get a negative result, which means it's decreasing. Right? That's what we're kind of anticipating. If I can get my keyboard to work. Okay, we got our negative, right? Okay. So we got a negative result here, so that means the original function is decreasing. So if our function is going from increasing to decreasing, then that means that here we have, that's how we can confirm that this is indeed a max, right? Okay, so then we can stand by this result, right? And so this was a good example where, you know, we couldn't just automatically jump straight to the second derivative because, I mean, we could, but that's going to be a lot to try to do the second derivative here, right? It's just extra work. And it was much easier to just use the first derivative test where we choose a point on the left, choose a point on the right. For this to be a max, the original function has to go from increasing to decreasing, okay? So then the maximum value, I guess I'll just get rid of all of this. So then we need the original function. We need to put 25 into the original function. Oh, we're almost out of here, guys. We're almost done. I don't know. I know it's a little intense. You just, you know, you have to do your best. You have to try. Okay, let's see. So we're going to say C. Oh, come on. C of t equals 25t times e to the power of negative 0.04t. Okay. Then we're going to say C of, I think we got what, 25? So the max concentration is at 229, all that, nanograms per milliliter, all right? Let's see. So then, see if after 25 minutes, the max concentration we get was 229.9240. Let's go 9247. The units, nanograms per milliliter. After 25 minutes. Okay. I'll just highlight it. So we got like this, we got like this. Those are the two pieces of, that's the information that we got. Sorry, I know it's a lot going on here. Let's go to view, single page. Okay. All right, so we got this. All right. So first find the critical values by taking their derivative, right? We did that. Set it to 0. We got 25. Is a critical value. Evaluating C of 25, we get the 229.92 nanograms per milliliter. Using the second derivative, now they did go ahead and do the second derivative, which is fine. You should, if you want that to be a max, you should get a negative result there, right? So when you plug in the 25, you see they get a negative result, which means that confirms that it is indeed a max. In order to do the second derivative, we'd have to do the product rule a couple of times. We used the first derivative test, and we got the same result. Notice to the left of 25, the original function is increasing. To the right of 25, the original function is increasing. Okay. We're almost to the end of this guy. I don't want to keep you for no more than a little over 5 minutes. Let's go a little bit further. So then we have this theorem 10. Maximum profit occurs at those x values for which profit, right? R prime is equal to C prime, and R double prime is less than C double prime. Let me see, max profit. So if you have your revenue function, revenue versus cost, the rate of change of your revenue is equal to the rate of change of your cost. Okay. And what does that tell us? So then that's going to give us what? A maximum if the second derivative is less than. I'm just trying to conceptualize like how they got this. Let's just kind of go with it for right now. Okay. So let's look at this. It says promoters of international fundraising. Let me see the time. I don't know if we're gonna have the time. I'll do the best I can in 5 minutes. I really don't want to keep you more than 5 minutes. Okay, I think what I'm going to do for this one is piggyback off my prepared notes just because we're short on time. It says promoters of international fundraising concerts must walk a fine line between profit and loss. Like this. Especially when determining the price to charge for admission to closed circuit TV showings in local theaters. By keeping records, the theater determines that at an admission price of $26, it averages 1,000 people in attendance. For every drop in price of $1, it gains 50 customers. Each customer spends an average of $4 in concessions. What admission price should the theater charge in order to maximize the total revenue? Right? So let's try to get an expression for the revenue. Okay. It says at a price of $26, it averages 1,000 people in attendance. Every time the price drops by $1, it gains 50 customers. Okay. All right. So we're thinking like, okay, we got our $26. That's the price. And we have an average of 1,000 people. But every time that price drops by $1, we gain 50 people. So we're going to capture the number of people. We're basically saying, so for the max revenue, we're going to say the number of people times the price of each ticket, plus the number of people times the money they spend on concessions. To capture the number of people, we're going to say the $1,000 plus 50 times X, right? And the X being each dollar decrease in the price of the ticket. So again, to capture the number of people, we're going to say the $1,000 plus 50 times X. To capture the price, we're going to say $26 minus X, right? So if X is 1, then now the cost is $25, and we should gain 50 people towards the attendance, right? If it's 2, now the price is $24, and we should gain 100 people, right? So that's how we capture those two. And then for the concessions, we're still going to use that 1,000 plus 50x. Let me see. It says each customer spends an average of $4 on concessions. Let me think about it. I think it's just the number of people, that 1,000 plus 50x. I think it's just times 4, right? Let's look at our prepared notes. We're going to use that. Okay, here. So again, let X be the number of dollars by which the price should be, the $26 should be decreased if X is negative, blah, blah, blah. So then the revenue is going to be the revenue from the tickets plus the revenue from the concessions. From the tickets is going to be the number of people times the price of the tickets. For concessions, it's going to be the number of people times 4, right? So then here, right, this is what we were talking about. Again, for the number of people, we capture that you have your average of 1,000 plus 50 times each dollar decrease in the price of the ticket, right? So this is going to be the total number of people. This is going to be the price of the ticket, $26 minus X, where X could be 1 or 2 or 3, whatever we're decreasing it by. And then from the concessions, you still have the same expression for your number of people, but then each of those people, each person spends an average of $4, right? So we just say times 4. So then we expand this out, right? You expand it all the way out. Ultimately, you'll get here. So then I think if we want to maximize the revenue, once we get to this point, the hardest part is this is going from here to here, right? Is this part. But once we get that, then here, if we want to maximize the revenue, oftentimes we take the derivative, set it to 0, and we can see it here. R prime, set it to 0, we get x equals 5. Since there's only one critical value, we can use the second derivative. So the second derivative is going to be negative, right? It's going to be the negative 100, which means that this is a max. So basically what we're saying is if we reduce the price of the ticket by $5, that's going to maximize our total overall revenue, right? So it's always negative. So this is the maximum revenue. So the theater should charge $21 per ticket. That is a really interesting case. I really enjoyed that one. I'm not going to lie. I definitely had to look at that one. I mean, I didn't have to, but I did look at it in advance because I remember in the past, it definitely tripped me up a little bit. It was a little bit weird the way it was worded, but that's why we have these sessions to think about it. I'm not trying, again, with this experience, I'm not trying to go hard. I'm really just trying to introduce these concepts to you and give you the space to kind of think about it at your own rhythm and rate. We got all semester now. Obviously, we're at the halfway mark, but again, the main structure, the main intent or design behind my structure is just to encourage you guys to I just really want to expose this information to you with it's not so rigorous where I'm giving you minimal information in a testing environment. I'm not trying to be like that. I'm just trying to be okay, this is what we're talking about. Let's try, just keep trying. It's okay. I'm really just trying to be kind of light and encourage you to try. Okay, I feel like there should be questions. I don't know if you guys, if you're still there, you are a trooper, right? My hat's off to you. Let me pause for the calls. Would you guys like to ask any questions before we go our separate ways? All right. Okay. Let me go ahead and make a copy available of anything that you saw me writing. Right here, calculus, notes. Okay, handwritten notes. All right. So when this bar finishes loading, you'll receive a copy of anything that you saw me writing. If there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy your evening, guys, okay? Keep up the good work. Keep trying. Keep pushing. I encourage you guys to collaborate, work together, work with the tutors, ask me questions, by any means necessary, get this stuff done, okay, guys? All right, enjoy your evening. Take care. Peace. Right here. Okay.